Good day, everyone, and welcome to this course on battery management systems. This model is designed to give you an introduction of the core components of the batteries and their management systems, which are crucial for modern energy solutions and electromobility solutions as well. This is the agenda of this first module. We will start with an introduction of electromobility and the basics of how the battery cells work, setting the foundation for understanding the whole battery systems. Then we will move and we will explore the key battery parameters such as the capacity, the energy density, the power, its voltage, and how all of these parameters will define the battery performance. Next, we will discuss the role of the BMS, the battery management system, and how it ensures the safety and efficiency of the whole system, as well as what are the main components that conforms it. Finally, we will look at the different ways the BMS systems are structured, what are the topologies, and how each of these topologies is tailored for specific applications. So let's begin with the introduction and the operating principle of the cells. As you may know, and as may you have felt it already, electromobility is completely transforming the way that we transport nowadays. This figure over here shows us the share of electromobility, and as you can see, by 2030 it is predicted that 50% of new cars that are being sold worldwide will be electric. That's a huge change, and it's a huge change that is happening in a very short period of time, especially if we consider that 12 years ago the electromobility was just an idea with few proof of concepts introducing to the automotive industry this possibility of having a sustainable carbon-free mobility and zero emissions. This change comes with several opportunities, but also comes with several challenges. As you can see on the right, one of the biggest differences between the traditional vehicles and the EV lies in the complexity of the system. An internal combustion engine, for example, has approximately 1,400 parts, while an electric motor only has 50 parts. In total, in the vehicle, 2,000 parts are eliminated in the EV systems. This has many advantages. We simplify the maintenance of the vehicles, and also we reduce the probability of having mechanical failures. On the other side, what is happening is that we are shifting the focus from the mechanical components to the electrical and electronic components. And because of that shift that we are having, the batteries become the heart of the EV, alongside with the battery management system that is acting as the brain of the battery. The implications of this shift are important and go beyond the automotive sector. All of the knowledge that the automotive industry has gained in battery development is now also applied to energy storage systems, for example, systems that are used for renewable energies or backup applications. So most of the content of this course is applicable for both sectors, and you can easily extrapolate what you will learn either in an electric vehicle or in an energy storage systems. And just to complete this first introduction, I just want to raise an important question to all of you. How are you adapting and how are you preparing for this new electrified world? Great, so now that we have set the stage with the rise of this electromobility, let's take a closer look of what the basic of the EV, the basic structure of an EV looks like. Understanding how the EV is built will help us to appreciate what is the critical role of the battery and what is the role that the BMS plays in those systems. Here we have the structure of the vehicle and the main components of it. We have First, the charging connection of the vehicle, and then at the core of every EV, we have the high voltage lithium-ion battery. This is basically where the energy is being stored, and essentially it is the fuel tank of the vehicle. Then this energy is managed and distributed to the electric motor that is over here, number 4. The electric motor has the function to convert the electrical energy into mechanical energy to be able to drive the wheels of the vehicle and to propel the vehicle. Supporting the battery and the motor, in the middle we have the power electronic systems, and specifically we have the inverter. The function of the inverter is to convert the DC power from the battery into an AC power to the motor. Without this system, without the power electronics that are in the middle, the energy transfer wouldn't be possible. Alongside with the battery, that is number 2, we have, of course, the battery management system that is inside of the battery, which is often, as I mentioned, referred to as the brain of the battery. The BMS has the function to monitor the battery health, to manage the energy output, and the most important is to ensure that all of this operates within safe limits. It is crucial to preventing any issues like overcharging, overheating, or cell imbalance, for instance, which can compromise safety and performance of the vehicle. The EV also has some auxiliary systems like the low voltage battery, that it is number 10 over here, that is mainly used to supply auxiliary loads like, for instance, lighting or the windows or safety systems. We also have one very interesting feature, that is the recuperative braking system. This system recuperates energy lost during braking and feeds it back into the battery. So it basically charges the battery when we are braking or when we are in a hill. As you can see here, the battery is the biggest element, is the heaviest, and also it is the most expensive component in the whole vehicle. It means that it is also the component that has more room for improvements and that we need to optimize the most. So it is the reason why there are so many research and so many innovations along the battery, along the safety of the battery, and along the battery management system. So, to get to understand how to optimize the battery and how to make better, more efficient and more safe vehicles, we need then to understand how the battery cells work. The battery cell is the smallest and the most essential building block of the entire battery systems. The core function of a battery cell is to store the energy. The battery cell is an electrochemical system that can store the energy in the chemical form, and then it releases it as electricity whenever it is needed. As you can see here, the battery cell is designed around 4 critical components. We have the active material, we have the electrolyte, current collector, and separator. I will give you a short definition of each of those so you can understand how actually it is built. So we start with the active material. The active material is found both in the anode and in the cathode of the battery cell, and basically is where the energy is being stored. Here, all the lithium-ion reactions and the chemical processes are taking place, and this is what allows the cells to store the energy, to charge, and to discharge efficiently. Then we have the electrolyte. The electrolyte, usually it is liquid electrolytes, and its function is to facilitate the movement of the lithium ions between the electrodes, so to facilitate the transportation of those lithium ions and to act as a bridge for the energy transfer. We also have the current collectors that you can see over here. I'm highlighting. The current collectors, depending if it is in the anode or in the cathode, it have different materials. Usually in the anode sides we use copper foils, and in the cathode sides we use aluminum foils. And the function of this is to conduct the electrons from the battery cell to the external circuit, enabling the cell to power any external system that we connect to it. And finally, we have the separator. The separator prevents the direct contact between the anode and the cathode and ensures that the battery cell in general operates safely without allowing the pass of electron from one side to another. This slide shows the physical structure of the cell that we described previously. Lithium-ion cells are available in three main formats: pouch cells, round cells, and prismatic cells. Despite of the external structure that they may have and the geometry and any physical dimensions that you can see over here, all of these formats share the same core internal structure that it is depicted here. The cells are conformed, or they are based on different layers that will create a sort of a sandwich, as you see. In the external layers, we have the current collectors, one from the anode and one from the cathode. Then we have the active material. We have an active material for the anode, and we have also another active material for the cathode, that, as it was mentioned, is the one that is where the chemical reactions are happening. All of this material is filled with the liquid electrolyte to facilitate the movements of the lithium ions. And in the middle, you can see the separators, that is the one that avoids the transfer of electron from one side to another. So let's understand the general operating principle of the lithium-ion cell and how all of these components work together. So as was explained, the cell function is to convert electrical energy into electrical energy, to convert chemical energy into electrical energy and vice versa. And all of this is possible thanks to the movements of lithium ions and electrons. Inside of the cell, there is going to be a flow of lithium ions between the electrodes. These ions can move inside thanks to the electrolyte, and this is what allows us to generate the electrical energy, which is then used to power the external systems. Here, the separator plays a crucial role, since it ensures that only the lithium ions can go from the anode to the cathode, but the main function of the separator is to avoid the flow of electrons. What it happens is that when the lithium ions are moving, the separator forces the electrons to move through the external circuit, that is the load or the charger that we are connected. The key of the lithium-ion cells is that this principle is reversible, so we can both deliver energy to these external circuits during discharge, but we can also restore that energy during charging. Specifically, to see how it works, during charging, that is the first one and the first plot that we see over here, the energy is supplied to the cells by means of this external circuit. This energy drives the lithium ions from the cathode to the anode. So it's the movement that that is represented by this arrow in top of the separator. While during the discharge process, the opposite happens. So the battery in the discharge process is delivering the energy to power the external device, and during that the lithium ions will move in the opposite direction. So the lithium ions will be moving from the anode to the cathode, and all of this thanks to the electrolyte and to the separator then. So as was mentioned, the batteries come in different formats that are here depicted a little bit more in detail. All of these formats share the same working principle as well as the same physical structure. However, the choice of the format affects the different factors. Depending on the cell format that we decide to use in our system, we will have different energy densities, we will have different mechanical stability, and the thermal performance of the battery will be also different. These three formats are universal, and based on this, manufacturers can scale up the cells into modules and packs and to create very modular systems. As I mentioned, each format is designed to meet specific requirements for energy density, mechanical stability, and flexibility for the whole application. I want to briefly compare and tell you which format is used better in which application. Maybe as reference, as you can see here, all of these vehicles, or in general EVs, can be built upon different formats. We have here one example of vehicle for each of these formats. However, the selection will strongly depend on the specifications of the vehicle itself. First, we have, for instance, the pouch cells. The pouch cells are the ones that have the highest energy density. They are very lightweight and they are very versatile in the design. In the pouch cells, usually the enclosure of the battery is aluminum foil, and because of that you don't have a stiffness in the housing. It is not very it does not have a lot of mechanical strength, but it's the same reason why we have so much high energy in a smallest space, and also why it is so lightweight. The problem with this is that they are maybe a bit difficult to stack, and also is that the system itself has a swelling mechanism. So when you are charging and discharging, this aluminum foil may expand and contract a little bit, so you need to create the mechanical enclosure to avoid that to be a problem. Then we have the cylindrical cells or round cells. These cells are very mature in the manufacturing process, what makes them also very cost effective, and they are used in several applications. One of the reasons is because they have a very high durability. And the problems with them is that as they have round cells, when you have an array of them, there are many empty spaces that you left open, and that creates a very inefficient usage of space. That what means that you have a lower energy density, and the pack itself will be less dense. Finally, we have the prismatic cells that are these ones over here, and I will say that they are a middle point between the high energy density of the pouch cells and the round cells. These are compact, the prismatic cells are compact. They have an efficient use of space, so they are a good balance between the density and the mechanical stability. However, they are a little bit more cost, they're more expensive than the cylindrical cells, and they are also less robust than the cylindrical cells. So, just to conclude, in this part, all of these cells are used in various electric vehicles, and there is a trend right now about having a high energy density, which is pointing us to use pouch cells in those vehicles. The performance of the lithium-ion cell, the safety and the lifespan of the battery depends heavily on the chemistry used in each application. When we say the chemistry of the battery, we are referring to the combination of all the materials that are used in the active materials and in the electrolytes. It means the materials that are used in the cathode, in the anode, and all of those materials at the end will determine the battery characteristics. Each chemistry is optimized for specific applications, and they will be balancing between the density of the energy, the amount of power the battery can deliver, how much time we can use it, what is the lifespan, how safety is the battery, and what is going to be the cost of the battery. For example, if we look at the batteries that are in smartphones, in that application particularly we will be prioritizing the compactness of the battery, and also we will have very high energy density. However, if we look at the batteries that are used in the electric vehicles or in the energy storage, we will focus on the durability and the safety more than, and we cannot achieve as high energy densities as, for instance, a smartphone has. Following that, I'm showing in this slide the different chemistries, and you can see the applications, the benefits, the disadvantages, and also a small diagram summarizing the advantages and disadvantages of each of those. So we begin with the lithium-ion cobalt oxide. This battery is commonly used in consumer electronics, for instance, as I mentioned, in the smartphones. It has a very limited lifetime. It's not tend to last longer, but it has a very high energy density. On the other side, for instance, we have the lithium-ion manganese oxide that is used to power, for instance, power tools, medical devices. Also, it is used in some electric vehicles and consumer electronics. One of the things that this chemistry offers is that it has fast charging capabilities. It also has a very good thermal stability, but if you can see, the lifespan of this battery cell and this chemistry is also reduced. Then we have the LFP battery cell. The LFP is very commonly used in energy storage systems and also in some EVs. And it is known because it has a very long lifespan, as you can see over here. And it also has excellent safety capabilities. However, this comes with the trade-off of having lower energy density than their counterparts. So these are three over here. Let's move to the following three. Here, just to summarize, we have also the NCA and NMC that are the cells that dominate the EV and many industrial applications, because as you can see, they offer very high energy densities, they are very versatile, they are not very costly, and they can be, they degrade, for instance, faster than LFP, and also they are less safe and they are more temperature sensitive than LFP, but they have a very good general trade-off between all of the different aspects of the battery cells. And finally, to conclude with this initial introduction to the battery cells, let's examine the discharge curves of the lithium-ion cells. And these discharge curves that we are seeing here at the end represents how the voltage of the battery cell changes as we discharge it. It means as the battery is delivering the energy over time. This curve is very helpful to analyze the battery cell's behavior, because it provides us insights, for instance, of their efficiency, the characteristics, the chemistry that we are using, and so on. So here we have in the x-axis the capacity of the cells, plot against the voltage of the battery cell. Some of the typical characteristics of the battery cells is, for instance, as you can see, that they almost all of them, or a general characteristic is that they have flat voltage range over here. The lithium-ion cells exhibit a relatively flat discharge curve, as you can see, during most of their operating range. This means that the voltage stays almost constant as the battery is delivering energy, and that is a very good feature in application, for instance, of EV. But we can also see that the cells have this exponential range that is over here. As the battery is approaching to the end of their capacity, so it means that it is getting close to an empty state, the voltage drops exponentially. This sharp decline basically is signaling us that the battery is almost empty. And in the same way, in some of the curves, if we look close to the state where the battery is fully charged, it also has this exponential curve. Something that we can also see over here is that different chemistries will exhibit different discharge profiles. We can analyze, for instance, that the LCO, the NMC chemistries have a relatively flat discharge curve, and that is what makes them also very good for applications like EV. We can also see that the LFP has a slightly lower voltage, and it is very known because it has also a very flat voltage range, and as I mentioned, it's also very safe. And that is the reason why this is very popular in energy storage and backup systems. In general, all of these profiles are crucial for selecting the right chemistry and to be sure that we are having the optimal performance and the optimal efficiency specific for each application. Later on in this course, we will see how the different chemistries and how all of these discharge parameters will be related to the requirements of the battery management systems. But so far, I think we have a good introduction of the battery cells.